All right, so you're getting ready for some system design interviews. But we're going to dive deep into these excerpts you've got here from Grokking, the system design interview.
Yeah.
Hopefully we can help you really nail those tricky questions.
Sounds good.
So, system design interviews, they can be a little intimidating.
It can be, yeah, even for experienced engineers.
Like the source material mentions, most people don't have experience building these massive systems in real life.
Yeah.
And the interviews themselves are kind of unstructured.
Yeah, and plus people just don't prepare enough.
Right, but acing these interviews, I mean, it can really lead to some pretty sweet offers, right?
Absolutely. It shows that you can think big, handle complexity, which is really valuable in the tech world.
Yeah.
The cool thing is just like coding interviews.
Yeah.
You can totally prepare for system design interviews.
So, okay, what's the best way to actually approach these system design problems? I'm all about, like, frameworks and steps, anything to make it less intimidating.
So the source lays out a really solid iterative process.
Okay.
It all starts with really understanding what you're building.
Oh, you mean like figuring out the requirements?
Exactly.
All
It's
right.
like, laying the foundation for a house. You can't start building without knowing how many rooms you need, what kind of features you want.
Right.
The source uses a Twitter example, so
Okay.
before you jump into designing, you need to ask things like, will tweets have videos? Are we just building the back end or the front end too? Do we need to show trending topics?
So even though those questions seem kind of basic, I guess they have huge implications on the design.
Totally.
Yeah.
Once you've nailed down the requirements, you move on to defining the system interface.
Go ahead.
Think of it as the blueprint that ensures that all the parts of your system can talk to each other.
Mm-hmm.
In the Twitter example, this means defining APIs like post tweet and generate timeline.
So it's like setting the rules of the game before everyone starts playing.
Exactly. And then comes the slightly scary part, back of the envelope estimations.
Yeah, I saw that in the source material,
Yeah.
capacity planning and all that.
Right.
Seems like a lot of math.
It's not about being perfectly precise at this stage.
Right.
It's more about showing that you can think at scale.
Okay.
So, how many users can this handle? How much data are we going to store? What kind of traffic are we expecting?
Gotcha. So it's more about showing that you can kind of handle that big picture stuff.
Precisely. Once you have a rough idea of the scale, you can start mapping out your data.
Okay.
The source emphasizes understanding data flow, like what information do we have and
Yeah.
how does it move through the system?
So it's kind of like creating a map of like the information landscape.
That's a great way to put it.
Okay.
So the source uses Twitter's data model as an example. You have users, tweets, and the relationships between them.
Okay. So we've got the requirements, the interface, the data, all kind of figured out.
Right.
What's next?
So now it's time to design the system architecture, like the big picture of how everything fits together.
Okay.
The source talks about breaking down the system into core components.
Mm-hmm.
They use the example of shortening a URL and showing how a request would flow through the system.
So it's kind of like a flow chart.
Exactly.
Yeah.
You identify the key building blocks
Got it.
and how they interact.
Gotcha.
And then you zoom in on each of those building blocks and
Yeah.
design them in detail.
Okay.
This is where you get into the nitty-gritty of how to distribute data, manage traffic, and make sure everything runs smoothly. The source draws parallels with real-world services used like TinyURL
Okay.
and talks about strategies like data partitioning, load balancing, and caching.
Okay. So I'm starting to see the big picture here. We go from clarifying what we're building to how it talks, understanding the data,
Yeah,
sketching out that big picture, and then getting into the details of each piece.
that's a great summary. Having this framework in mind will definitely help you tackle any system design problem thrown your way.
Awesome.
Now, let's see how these principles actually apply to some popular services that you're probably familiar with.
Sounds good to me. I'm ready to get specific.
All right, so your source material dives into several examples,
Yeah.
but let's focus on the ones that seem most relevant to you.
Okay.
How about we start with URL shortening, using TinyURL as a case study?
Perfect. Let's shorten our way to understanding system design.
One clever thing that TinyURL does is pre-generate those shortcodes offline.
Oh, huh?
Instead of encoding the URL on the fly every time, they have a stash of random 6-letter strings ready to go, which makes things super fast.
Oh, that's clever. Like having a bunch of pre-addressed envelopes just waiting for the content.
Right.
The source also mentioned using the 80-20 rule for caching. So catching those super popular URLs, that really boosts performance, huh?
Right. It's all about understanding those usage patterns
Yeah.
and optimizing for them. Speaking of which, let's move on to Pastebin.
Okay.
It seems pretty similar to URL shortening at first.
Yeah.
But there are some key differences.
So even though they both involve, like, storing and sharing content,
Right.
those differences, they lead to different design choices.
Exactly.
Yeah.
So the source talks about how the choice of database, whether it's a relational database like MySQL or a distributed key value store, it really depends on the kind of data that Pastebin handles.
It's like choosing the right storage container for your stuff. You know, like a filing cabinet for your important documents.
Right.
But maybe just a big bin for, like, random knickknacks.
Now, how about we level up the complexity a bit and look at Dropbox?
Bring it on, file syncing.
Yeah.
That seems way more complicated than just shortening some URLs.
So the source explains why Dropbox breaks files into chunks for transfer and syncing.
Okay.
It makes things much more efficient, especially when you have large files.
It's like sending a package in multiple boxes instead of one giant one.
Right.
Easier to manage and less likely to get lost.
And speaking of efficiency, the source also dives into the trade-offs between different cache writing schemes, write through, write around, write back. Each one balances performance with the risk of losing data if something goes wrong.
So it's like choosing between different delivery methods. Do you want the fastest option?
Right.
Or the one that guarantees your package won't get lost?
Right.
Even if it takes a bit longer.
And finally, let's circle back to Twitter.
Okay.
Remember all those design considerations we talked about earlier?
Yeah.
Well, the source gets into the specifics of how they handle things like sharding.
Oh, yeah, I remember that term.
Which is about distributing data across multiple servers.
Right, and that's especially important for social networks where you have, like, some users that have tons of followers and generate a ton of content.
Exactly.
Yeah.
And they also have to choose how they're going to deliver those updates, whether it's a pull model where users request updates or a push model where the server sends them out automatically.
It's like deciding whether to constantly check your mailbox for new mail or just wait for the mailman to deliver to your door.
Right. Each approach has its pros and cons.
Yeah.
Now, before we move on to some broader system design concepts,
Okay.
what stands out to you so far?
Honestly, it's just amazing to kind of peek behind the curtain and see how these services we use every day actually work.
Yeah.
It's like seeing the intricate gears and mechanisms of a clock for the first time.
That's a great observation.
Yeah.
And it highlights a really crucial point. These are real-world examples of how the principles we talked about earlier get applied.
Right.
It's not just about memorizing specific solutions.
Yeah.
It's about understanding the underlying concepts and adapting them to different scenarios.
Right. It's like learning to cook.
Mm-hmm.
You know, you might start with a recipe, but eventually you understand the techniques and you can create your own dishes.
Exactly. Now let's build on that foundation and explore some broader concepts that go beyond specific services and dive into some really fascinating stuff.
All right, I'm ready.
Let's do it.
Okay, so we've gone through some real-world examples of system design in action.
Yeah.
Now, let's zoom out a little, look
Wow.
at some broader concepts that apply to a bunch of different scenarios.
That's good.
So your source material dives into this fascinating topic, distributed systems,
Right.
which is all about spreading the workload across a whole bunch of machines. It's like having a team of workers instead of just one,
Yeah,
each one handling a part of the task.
exactly.
Okay, but how do you make sure all those machines are working together smoothly?
Well, that's where those key characteristics of distributed systems come in.
Okay.
Scalability, reliability, availability, efficiency, and manageability.
Okay.
The source breaks these down, and
Yeah.
they're all about ensuring that your system can handle growth, withstand failures,
Yeah.
and just be easy to operate.
Okay, let's unpack this a little bit. What about scalability?
Okay.
I hear that term thrown around all the time.
So scalability basically means your system can gracefully handle increased load.
Okay.
The source differentiates between horizontal scaling, like adding more machines, and vertical scaling, which is like beefing up the existing machines.
So adding more lanes at the grocery store versus like upgrading the existing ones with a super fast cashier.
Exactly.
Gotcha.
So each approach has its pros and cons.
Then there's reliability.
Right.
Yeah.
Reliability is all about ensuring your system keeps working even when things go wrong.
Right. Because no system's perfect.
Exactly.
So you have to plan for those hiccups, right?
It's like having a backup generator kick in if the power goes out.
Okay. And then there's availability, which is kind of related to reliability.
Right. Availability means your system is accessible to users whenever they need it.
Gotcha. So reliability is like keeping things running internally, and availability is making sure users can always access the service.
You got it. Then there's efficiency, which is about making sure your system uses resources wisely and responds quickly to requests. It's like optimizing traffic flow on a highway.
Okay.
You want cars to move smoothly without creating bottlenecks.
And lastly, there's manageability, which I guess means making sure that your system's easy to operate and troubleshoot.
Exactly. It's about having clear instructions and well-organized tools so that even if something does go wrong, you can easily find and fix the problem.
Okay, so all of those characteristics make sense.
Yeah.
But designing for all of them at the same time, it seems like a tall order.
Well, that's where things get even more interesting.
Oh, boy.
The source introduces this fundamental concept called the CIP theorem.
Oh, yeah, I remember this from earlier.
Which basically says that you can't have it all in a distributed system.
It's like that triangle where you can only pick two sides.
Exactly. So consistency, availability, and partition tolerance.
Yeah. Remind me what those terms mean again.
Okay, so consistency means all users see the same data at the same time, even if they're accessing it from different machines. Availability, as we discussed, is about ensuring the system is always accessible.
Right.
And partition tolerance means the system keeps working even if communication between different parts of the system is disrupted.
So it's like choosing between having a perfectly synchronized choir, a show that must go on no matter what, or a team that can still perform even if some members are out of touch.
Tough choices.
Yeah, tough choices.
And those choices have real-world consequences.
Right.
The source gives examples of how different systems prioritize different CHAP aspects.
Okay.
For example, a bankless system might prioritize consistency above all else, even if it means temporarily sacrificing availability during a network outage.
Okay.
On the other hand, a social media platform might prioritize availability, even if it means accepting some inconsistency in the data.
Makes sense. It all depends on the needs of the system.
Right.
Speaking of trade-offs, the source also dives into consistent hashing.
Yes.
Which is a technique for distributing data across multiple servers. It sounds kind of complex.
It's actually a pretty clever idea.
Okay.
Imagine a ring where each server occupies a segment. Data is mapped to specific points on that ring using this special function.
Okay.
When you add or remove a server, only the data in its segment needs to be redistributed.
Gotcha.
Which minimizes disruption to the rest of the system.
So it's like adding or removing chairs in a circular theater without disturbing the entire audience.
Exactly.
Pretty neat. Now let's shift gears to another crucial aspect of system design. Choosing the right database for the job.
Okay.
The source material dives into the classic SQL versus NoSQL debate.
Yeah, that always seems to come up.
Right. I'm still trying to wrap my head around the differences and when to use each one.
Me too.
It's a common dilemma.
Yeah.
But understanding the strengths and weaknesses of each approach can really help you make an informed decision.
Okay.
So SQL databases, they're like those meticulously organized filing cabinets.
Okay.
They're great for structured data and complex queries.
Yeah. Plus, they offer ACID properties.
Oh, yeah. ACID properties.
Which guarantee data consistency and reliability even when you have failures.
Okay, so what are ACID properties again?
So think of it this way.
Okay.
Atomicity means a transaction is either fully completed or not at all. Like transferring money between bank accounts.
Okay.
Either both accounts get updated or neither does.
Right.
Consistency ensures that the database always remains in a valid state.
Okay.
Isolation means multiple transactions can happen concurrently without messing each other up. And durability guarantees that once a transaction is committed, it's there to stay.
Right.
Even if the system crashes.
Wow. Those ECD properties.
Oh, yeah.
It's like a superhero team for data integrity.
They are pretty powerful.
Yeah.
Now, on the other hand, NoSQL databases are like those flexible storage bins that can hold all sorts of different things.
Yeah.
They're great for handling large volumes of unstructured data, like social media posts or sensor readings, and they scale horizontally really well.
So SQL is like the meticulous accountant.
Yes.
And NoSQL is the adaptable all-rounder.
Exactly.
But are there any downsides to NoSQL?
Well, NoSQL databases often trade off some of those ACD guarantees for performance and scalability.
Gotcha.
They might not be the best choice if you need absolute data consistency at all times.
So it's like choosing between a reliable but slow delivery service and a fast but occasionally unpredictable one.
You got it. The source emphasizes that there's no one-size-fits-all answer.
Right.
Choosing between SQL and NoSQL really depends on the specific needs and constraints of your project.
Yeah, that makes sense. It's all about choosing the right tool for the job.
Now let's talk about another important aspect of system design, handling real-time updates in web applications.
Okay.
The source material covers a variety of techniques, from traditional polling to long polling and WebSockets.
Real-time updates.
Yeah.
That's like trying to keep up with the latest news on a constantly evolving story.
Exactly. Traditional polling is like calling your friend every few minutes to ask if there's any news.
Okay.
Inefficient and annoying.
Yeah, and like constantly refreshing a web page to see if there are any new posts.
Right. Long polling is a little bit smarter. It's like calling your friend and saying, don't hang up until you have some news.
Okay.
So the server keeps the connection open until there's new data to send.
Gotcha.
Which reduces the number of requests and provides much faster updates.
So it's like having a dedicated line open to the newsroom. You get the updates as soon as they happen.
Right. And then there's WebSockets.
Okay.
Which are like having a live video chat with your friend.
Cool.
It enables continuous bidirectional communication.
Wow.
So updates can flow back and forth instantly.
That sounds like the ultimate real-time experience.
It is.
But I guess that also requires a lot more resources on the server side.
You're right. Each approach has its trade-offs.
Right.
Traditional polling is simple but inefficient. Long polling is more efficient, but it can be more complex. WebSockets offer the best real-time experience, but require more server-side horsepower.
So it's like choosing between a megaphone, a walkie-talkie, and like a video conferencing system.
That's a great analogy.
Cool.
Now, we've covered a lot of ground in this part of the deep dive.
Yeah, we have.
We've explored those key characteristics of distributed systems, revisited the CAP theorem, tackled consistent hashing, delved into the world of SQL versus NoSQL databases, and real-time updates.
Yeah.
What are your key takeaways so far?
Honestly, it's a lot to process.
Yeah.
But I'm starting to see how all of these concepts are interconnected.
That's great.
Yeah, it's like learning the different instruments in an orchestra and how they come together to create a symphony.
That's a fantastic way to put it.
Yeah.
System design is about more than just knowing the individual concepts. It's about understanding how they relate to each other.
Yeah.
And using them to create a harmonious, functional whole.
I'm definitely feeling a lot more confident now. That's great. Yeah, it's like having this toolbox full of specialized tools and I know how to use them.
That's the spirit. Now let's take a short break, and when we come back, we'll explore some even more advanced techniques and strategies that will help you truly master the art of system design.
Okay, we're back and ready for the final part of our system design deep dive.
All right, so we've laid a really solid foundation. Now we can explore some of those more advanced concepts that'll really help you shine in those system design interviews.
Okay, what's first on the list?
Let's revisit those pull and push models for data updates we talked about earlier.
Oh, yeah?
Remember, it's about how clients get updates from the server.
Yeah, we talked about it with like social media feeds, right? Like, do you constantly check for new posts or does the platform send them to you?
Exactly. So the pull model is like checking your mailbox.
Okay.
The client has to request those updates from the server. The push model is like getting a notification. The server sends those updates to the client without being asked.
So pull is more passive.
Yeah.
Push is more proactive.
Exactly.
But I guess each approach has its pros and cons.
Definitely. Pull is simpler to implement.
Yeah.
But it can be inefficient if there are lots of updates.
Okay.
Push is more real-time, but can be complex and resource-intensive.
So it's like checking your email inbox every hour versus having those notifications pop up on your phone whenever you get a new message.
Right. Each method works, but they have different implications.
Exactly.
Now let's dive into a specific example of the push model, the publisher-subscriber pattern.
Publisher-subscriber, okay.
Yeah, it's a really common way to enable real-time communication between different parts of a system.
Okay, that rings a bell. Can you refresh my memory a little bit?
Imagine a newspaper publisher and its subscribers. The publisher creates content and the subscribers want to get that content.
Right.
But instead of the publisher sending every article to every subscriber individually, it uses a central distribution system.
So the publisher sends the articles to the central system.
Right.
And then the subscribers sign up for specific topics or categories that they're interested in.
Exactly. The distribution system, it manages the subscriptions and delivers the right articles to the right subscribers.
That's a great way to explain it. It makes things a lot more efficient, especially if you have lots of subscribers and lots of different types of content.
Right. And it decouples the sender and the receiver, meaning the publisher doesn't need to know anything about the subscribers and vice versa.
Okay, that makes sense.
So we've covered the push model and the publisher-subscriber pattern. What other advanced techniques should we have up our sleeve?
Well, what else?
Concurrency is a big one.
Okay.
It's about handling multiple things happening at the same time.
Right.
Which is super important for any system that deals with lots of users or lots of requests.
Concurrency. That sounds a little bit like juggling, keeping all those balls in the air at once.
That's a really good analogy. So imagine a busy intersection with cars coming from all directions.
Yeah.
Concurrency is like managing the traffic flow to prevent any accidents and make sure everybody gets to their destination smoothly.
Okay, I can see how that applies to system design.
Right.
You have all these different requests, processes happening at the same time.
Yeah. Yes.
And you need to make sure they don't conflict or cause any problems.
Exactly.
Right.
So the source material highlights several techniques for achieving concurrency, including locks, semaphores, and message queues.
Okay, locks, semaphores.
Yeah.
Those sound like tools for like a high-tech traffic control system.
Right. So think of locks as traffic lights.
Okay.
They control access to shared resources, ensuring that only one car can pass through the intersection at a time.
So locks prevent multiple users or processes from trying to modify the same data at the same time?
Exactly.
Which could lead to chaos.
Yes.
Right.
Semaphores are like traffic signs that indicate the available capacity of a resource. They allow a limited number of cars to pass through, preventing congestion and ensuring that the system doesn't get overwhelmed.
So semaphores are kind of like rate limiters.
Right.
They control that flow of requests.
Exactly.
Yeah.
And then there are message queues.
Okay.
They're kind of like dedicated lanes for specific types of vehicles. They allow different parts of the system to communicate asynchronously.
Okay.
Meaning they don't have to wait for each other to finish before proceeding.
So message queues are kind of like email inboxes. You can send a message and then just move on with your day.
Exactly.
You don't have to wait for that immediate response.
Each of these concurrency techniques has its own strengths and weaknesses.
Yeah.
And the best choice depends on the specific requirements of your system.
Right.
The source material provides some great examples of how they can be applied in real-world scenarios.
Okay, so concurrency definitely seems like a crucial concept to master for system design.
Is.
What else should we be thinking about?
Well, we can't forget about security.
Right, of course.
It's a fundamental aspect of any system design.
Yeah, especially these days.
Especially in today's world where those cyber threats are becoming increasingly sophisticated.
It's like building a fortress to protect your valuable assets from attackers.
Right.
Right. You can't just focus on making the castle beautiful. You got to make sure it's secure.
Exactly. So the source material highlights some key security considerations, including authentication, authorization, data encryption, and input validation.
Okay, so authentication and authorization.
Right.
They're like the guards at the entrance to the fortress, checking IDs and granting access only to authorized personnel.
Exactly. So authentication is about verifying the identity of a user or process.
Okay.
And authorization is about determining what actions they are allowed to perform.
Okay, and then data encryption is like putting the crown jewels in a vault with multiple locks.
Right.
It's protecting that sensitive data from prying eyes.
Exactly. And then there's input validation, which is like inspecting packages for explosives before they enter the fortress.
Right, so it's about filtering out anything that looks suspicious or dangerous.
Right. It prevents malicious data from sneaking into the system and potentially causing harm.
So it seems like a multi-layered approach to security is really important.
It is.
Yeah.
And the source emphasizes that security should be baked into that system design from the very beginning.
Yeah, not just like an afterthought.
Not tacked on as an afterthought. It's like building the fortress with security in mind from day one rather than trying to add those defenses later when it's already vulnerable.
Right. Makes sense.
Now let's talk about another crucial aspect of system design, testing.
Testing, okay.
It's about making sure that the system works as expected, identifying and fixing defects, and ensuring that it can handle real-world scenarios.
It seems like a no-brainer.
Yeah.
But I guess it's easy to overlook when you're excited to get the system up and running.
It's definitely tempting to skip ahead, but testing is essential for building a reliable and robust system.
Yeah.
Imagine building a bridge without conducting any stress tests. That would be pretty risky.
You want to make sure it can handle all that traffic before letting anyone drive across.
Exactly.
Yeah.
So the source material highlights different types of testing, including unit testing, integration testing, system testing, and performance testing.
So unit testing is like testing each individual component of the bridge in isolation.
Right.
Making sure those beams and cables are strong enough.
Exactly.
Integration testing is like assembling the bridge and making sure all the pieces fit together and work properly.
Right.
System testing is like driving a car across the bridge.
Yes.
See how it performs in real-world conditions?
Right.
And then performance testing is like measuring how much traffic the bridge can handle before it starts to buckle.
You got it. Testing should be an integral part of the software development lifecycle, not just a final step before release.
It's like conducting those inspections throughout the entire construction process,
right,
rather than just waiting until the ribbon-cutting ceremony.
Well, it seems we've reached the end of our system design deep dive.
Oh, wow, that went fast.
I know we've covered a lot of ground.
We have.
From the fundamentals to some pretty advanced techniques.
Yeah, I'm feeling a lot more equipped to tackle those system design challenges now.
That's what we were hoping for.
Yeah, it's been an amazing journey, and I really appreciate you guiding me through it.
Of course.
I feel like I've gained a whole new perspective on how these complex systems are designed and built.
And remember, this is just the beginning.
Right.
There's so much more to learn and explore in the world of system design.
Yeah.
The key is to stay curious, keep experimenting, and never stop learning.
Absolutely. And to all of you listening out there, we hope this deep dive has given you the knowledge and the confidence to embark on your own system design adventures. So whether you're prepping for interviews or just want to understand how the systems we use every day are actually built, we encourage you to keep learning.
Keep building.
Keep building and keep pushing the boundaries of what's possible out there.
Absolutely.